Welcome to our exploration of two fascinating phenomena in physics: terminal velocity and Stokes' law. Imagine yourself soaring through the skies, weightless and free, as you embark on an exhilarating journey into the world of terminal velocity. Terminal velocity is the point where the forces of gravity and air resistance reach equilibrium, resulting in constant descent speed. But what factors influence this speed? We will delve into the factors affecting the terminal velocity, from the size and the shape of the object to the density and viscosity of the surrounding medium. Through mathematical analysis, we will uncover the secrets behind this essential concept in fluid dynamics. And as we explore terminal velocity, we will also untangle the mysteries of Stokes' law, a fundamental principle in understanding the viscous drag forces. So, get ready to soar to a new height and uncover the physics behind the thrill of terminal velocity. Stokes' law, streamlined shape in the vehicles are crucial for reducing the pressure drag. For a streamlined body, pressure drag is minimized because flow can reattach at the rear, resulting in improved efficiency and performance. When a solid object moves through a viscous medium like air or water, it encounters resistance known as viscous drag. This force arises due to the interaction between the object surface and the molecules of the medium. It is fascinating to note that this drag results in continuous loss of energy as the object progresses through the medium. Engineers combat viscous resistance by employing the aerodynamic principles in designing the vehicles such as the cars and airplanes. By crafting a streamlined shapes, they aim to minimize the drag force. This streamlined design allow for the smooth airflow around the vehicles, reducing the energy required to overcome the resistance and enhancing overall performance. Stokes' law provides a mathematical representation of viscous drag on a body moving through a viscous medium. This law states that the viscous drag force acting on a spherical body characterized by its radius r, velocity v, in a medium with the viscosity eta can be calculated using the formula force viscous is equal to 6 pi eta rv. Stokes' law serve as a crucial tool in understanding and predicting the behavior of object immersed in viscous fluid. It allows engineers to quantitatively analyze the effect of viscosity on the drag force experienced by the objects, aiding in the designing and optimization of various systems and devices. Pressure drag differs between a spherical shape and a streamlined shape. When a sphere moves through a viscous medium, it creates a wake of disturbed fluid behind it, resulting in pressure drag. In contrast, a streamlined shape is designed to minimize the pressure drag by smoothly gliding the flow of the surrounding fluid, thereby reducing the resistance and improving the efficiency in fluid dynamics. Terminal velocity is a fascinating concept in physics that arises when a body is driven by a constant force, such as gravity. Initially, when the body starts its descent, its velocity is zero, and the acceleration experienced is at its maximum. As the body gains speed, the viscous force acting on it steadily increases. As the viscosity continues to rise, there comes a point where the viscous force matches the force driving the body downwards, usually gravity. At this crucial juncture, the resultant force acting on a body becomes zero. Consequently, the body achieves a constant speed known as the terminal velocity. Some interesting facts about terminal velocity. Terminal velocity represents a state of equilibrium between the gravitational force and the viscous resistance. This balance ensures that the body descends at a constant speed without accelerating indefinitely or come to a halt. The terminal velocity of an object depends upon various factors, including its size, shape, mass, and the density and viscosity of the medium through which it falls. For instance, larger objects typically have higher terminal velocities due to their greater mass and surface area. Let's go through the real world application. Understanding terminal velocity is crucial in the fields such as skydiving, parachuting, and engineering. Engineers must consider terminal velocity when designing the objects like parachutes to ensure safe and controlled descents. Terminal velocity can be observed experimentally by dropping the objects of different sizes and shapes into a viscous medium such as liquid. By measuring the time taken for the object to reach the terminal velocity, scientists can analyze the effect of various factors on its descent. By understanding the concept of terminal velocity and its underlying principles, scientists and engineers can better comprehend the behavior of the object in motion and develop innovative solutions for a wide range of applications. Consider the downward movement of a spherical body through a viscous medium such as a ball falling through a viscous medium as a ball falling through a liquid. If r is the radius of the body, rho the density of a material of the body, rho 0 is the density of the liquid, then the weight of the body downward force is Fg equal to 4 by 3 pi r cube into rho into g. The buoyancy of the body upward force Fb is equal to 4 by 3 pi r cube rho 0 g. The net downward force is equal to 4 by 3 pi r cube into bracket rho. Net downward force is 4 by 3 pi r cube into bracket rho minus rho 0 bracket close into g. If v is the terminal velocity of body, then the viscous force F viscous is equal to 6 pi eta rv. When acceleration becomes 0, upward viscous force is equal to resultant downward force. Therefore, 6 pi eta rv is equal to 4 by 3 pi r cube into bracket rho minus rho 0 bracket close into g. On simplifying, we get v is equal to 2 by 9 r square g into bracket rho minus rho 0 into g divided by eta. Before we delve into solving some interesting problems, I recommend exploring need-based MCQs on www.genit.com for additional practice and preparation. Problem 1. The velocity of a small ball of mass m and density d, when dropped in a container filled with glycerin, becomes constant after some time if the density of the glycerin is d by 2. Then ask to find out the viscous force acting on the ball. When velocity is constant, it implies that acceleration is 0. It means downward force acting on the object is equal to upward force. F capital G is a downward gravitational force which is equal to Fb, that is buoyant force upward, and Fv, that is viscous force upward. Now, gravitational force Fg is equal to mass into gravitational acceleration, that is mg. Buoyant force is equal to volume of a liquid displaced into g into density of a fluid. The volume of a liquid displaced is equal to volume of the object, which is equal to mass capital M upon density small d. Therefore, Fb, that is buoyant force, is equal to M upon d into density of a fluid d by 2 into gravitational acceleration g. Therefore, Fb is equal to mg upon 2. On substituting the values, we get Fv equals to mg minus mg upon 2, which is equal to mg upon 2. Option 3 is correct. Problem 2. A solid ball of volume V is dropped in a viscous liquid. It experiences a viscous force F if the solid ball of volume 2V of same material is dropped in the same fluid. Then asked to find out viscous force acting on it in terms of viscous force experienced by earlier ball of volume V. We know that viscous force F viscous is equal to 6 pi eta RV. Therefore, F viscous is proportional to R. The volume of a ball V is equal to 4 by 3 pi R cube. Volume of a new ball, that is 2V, is equal to 4 by 3 pi R1 cube. Comparing both the volumes, we get 2 times of 4 by 3 pi R cube is equal to 4 by 3 pi R1 cube. Therefore, R1 is equal to 2 raised to 1 by 3 R. Therefore, new viscous force is directly proportional to R1. Replacing the value of R1 as 2 raised to 1 by 3 into R, we get new viscous force proportional to 2 raised to 1 by 3 R. Therefore, new viscous force is equal to 2 raised to 1 by 3 into F. As we conclude our discussion on mechanical properties of fluids, I, Avinash, from www.ginit.com, sign off. I humbly request you to like, share, and subscribe to our channel. See you in the next intriguing topic. Until then, take a deep dive into your niche syllabus and immerse yourself in the mystic wonders of nature.